Hi there. Today I would like to discuss a very basic problem of thermal calculations. Here you see we have a number of pairs of Rth and tau, which basically represent the Foster model parameters of a semiconductor combined with the heatsink. Now the system of semiconductor and heatsink is represented here to the left bottom part. On top we have the thyristor disk, and to the lower side we have the heatsink. For this total system, the pairs of the Foster model parameters are represented here. We have 6 pairs of Rth and tau, starting from Rth1, tau1, and all the way up to Rth6 to tau6. The target of this problem is to find out the temperature at the end of 4 seconds once the loss curve is given in terms of 2 pulse signals. That means at 0 seconds, a loss pulse of 500 watts are applied to the thyristor up to the point of 1 second, and then a 300 watts of power is applied to the thyristor up to 4 seconds. So basically it is a pulse of 2 different powers which are given for the specified time frame. The ambient temperature for this problem is assumed to be 35 degrees Celsius, and the target is to calculate the junction temperature at 4 seconds. Now, there are a couple of steps to go through the solution of this problem. As you are aware already, this is a Foster model, and since this is a Foster model, that means the analytical equation of these are represented using this Rth curve. This Rth curve is given here for 6 elements. Now you see these are the 2 parameters, as Rthn and tau-n. These are normally also given by the manufacturers, but in the chain form or the circuit diagram of this model is represented somewhat with Rth and Cth pairs. That means for the circuit representation we need to transform the time domain of the model to the capacitance values here. To do that, we can use the relationship of thermal time constants here. That means tau is equal to R times C, where tau is the thermal time constant, Rthn, which are the partial thermal resistances in terms of the pairs, are given already here in the problem description, and Cthn are the corresponding thermal capacitances. So using this relationship, we can calculate the Cth. Now, as from the equation, it is obvious that the curve of the temperature is going to be exponential. So the rise of the temperature we can see from the ambient temperature to a certain maximum value at point 1, because at this time 500 watts of loss is being applied. And then after 0.1 second, after this point of 1 second, the step of the power is reduced to 300 watts. So we will see another type of exponential curve. And the target is to find the Tj, or the junction temperature, at 4 seconds. I would like to now move back to the MATLAB lab script to walk you through the solution. At the very outset of the problem, I would like to initialize that the partial thermal impedances, which are running from Rth1 to Rth6. So these are the values in terms of degrees per watt, or also in Kelvin per watt. And then I built up a vector of the Rth elements of the 6 pairs. No, not 6 pairs, but 6 elements, which is then given a general name of Rth. Again, thermal time constants for this equation can be written as follows, also in terms of a vector here. So these are again tau 1, 2, 3, 4, 5, 6 are given values from the problem description. Since we want to calculate back to the capacitance, we need to take advantage of this division. That means CTH is equal to tau divided by RTH. And since this is a vector division or element-wise division, we need to introduce that point slash, that means dot division. If we have the pulse application, this one, if we have the power as pulse form, we can calculate the temperature of the semiconductor device at the end of each pulse using this relationship, which is given here. That means delta Tn is a new temperature after the end of any arbitrary pulse. Delta Tn naught is the initial temperature, could be at the beginning of the pulse. And using this relationship, we can calculate the temperature change at the end of each pulse. Now we can do it iteratively to find for each pulse that is applied in the waveform. Remember that if we want to calculate the temperature rise for a particular pulse, we also need to give the end value of the pulse, which is T1, and the start value of the pulse, which is T0. So these will keep changing depending on what pulse we consider. So for our case, since we will represent T0 as 0 seconds, T1 as 1 second, and T2 as 4 seconds in our scripts for the calculation. And also from the problem description, we have that ambient temperature is 35 degrees Celsius. I also define PV1 and PV2, which are the two different levels of the power step pulses here. So PV1 is 500, 0 to 1 seconds. PV2 is 300 watts between 1 and 4 seconds. As I mentioned, I defined the T0, T1, and T2 as 0, 1, and 4 seconds. Now this is time to implement this equation for each pair of RC elements or Rth-tau elements. That means we need to calculate for this circuit, for this pair, there would be a temperature rise or change in more general terms. For the second pair, there will be a temperature change. For a third, or so forth, it continues. And the total temperature change would be summed up to calculate the temperature of the junction. We will see how to do it now. So let's implement for the first pair of RC or Rth-tau the temperature change, which is at the beginning. We assume that there is no pulse applied. So the first pulse would be 500. So initially there is no pulse. And PV1 is applied. So this is a PV is there. Just keep looking on this equation first and you will understand instantly what I mean here. So PV1 is then representing PV, RTH-n, since n is a variable. So for the first element, first pair of Rth-tau, this is RTH1. Then we have 1 minus exponential form. Now, since we're calculating the temperature changes at the end of first pulse, and this pulse is time framed within T1 and T0, so we are using this time difference, T1 to T0. Tau 1, as I said, for 6 pairs, there will be tau 1 to tau 6. Once we're done here, we can also implement for RTH-tau 2 and pair 3, 4, and all the way up to the 6th pair of RTH-tau. And then let's also build up a vector of all the temperature changes, and here is the junction temperature at the end of first pulse. That means we have the ambient temperature plus the sum of all the temperature changes, as we just mentioned shortly. This will give us the junction temperature of the thyristor at the end of this first pulse. That means this peak would be then Tj1. Let's continue with the calculation further, because our target is to calculate the Tj, or junction temperature, at this point, at 4 seconds. Now, to calculate the temperature changes for the second pulse, we can consider the temperature from the first pulses. That means at the end of the first pulse, it will give us a temperature change, which will be the initial temperature for our second pulse. If you consider this curve again, if you come here at second one, so these initial temperature changes of each pair would be then used as an initial condition for the second pulse, which is exactly, you see here, the implementation of this formula as an iteration 2. So delta T1 is RTH pair T1, RTH pair 1, and 2 is for step or pulse step 2. So naming conventions, for the first pulse it was always 1, and 1, 2, 3, and all the way up to 6. These were the RTH pairs. Similarly, delta T1, 2 as a 2 here represents the second pulse, and 1 to 6 are the pairs of Rth-tau. So we take delta T11 as the initial condition for the first pair of RC, and then implement just this equation here, exponential of this. Now also be careful that we're using the time space of the second pulse, which is from T2 to T1. So the end time is T2, start time is T1, and the rest is similar, a repetition. And of course, since we have a different power level in the pulse, we use PV2. In the same case, if we sum of the temperature changes of each element with the ambient temperature, we get the junction temperature at the end of the second pulse. So if we run this file, we should be able to see the value. So we can see, let's clear the window, Tj1, which is 90.62 degrees Celsius, and Tj2 is 81.6 degrees Celsius. That means at 1 second we will have 90 degrees Celsius, and at 4 seconds we'll see 81 degrees Celsius. Let's do this same calculation in PLECS now, and to validate if our theoretical calculation would be the same also in the PLECS environment. It will also give you a more confident way of problem solving. Since I will be using the PLECS standalone version, I will still like to use the defined variables that I used just in my previous calculation. So I've taken over the values again to an M file, since I want to run this M script from inside the PLECS standalone version. So here is again this vector tau of partial thermal resistances. Here is the time constant, calculation of the capacitance. I'm defining two different variables here for initial temperatures. I'll come back to you to show you why. So let's say T initial temperature is 35 and T ambient, or ambient temperature, it is also 35 degrees Celsius. Here are again two powers with the given time references. This I will need to build up the source of the power. And there are some other variables for the simulation control. Let's now turn back to our PLECS environment. Control L to open the library browser. So for the simulation circuit, we'll need the thermal domain. So let's go to the thermal domain. We need some components. Heatsink we do not need because we will be using an external description of the thermal network. We need the thermal resistor, thermal capacitor. We need a meter, grounded meter. We need a power source. This is not the control one. This constant temperature, we will be having this for the ambient temperature. And we need a controlled, what was that? Controlled heat flow, yes. This is what we need. We will also need a step function from system. We need a sum block. Okay. Let's hide the name and continue building up that topology. I will build the poster model, that means the thermal part first. And there is only one part, thermal one, but I will show you later how to generate the pulse as well. So this one, if you go back to our M file, let's keep it to the left. You see, we already have built up a vector for that. That means we can take the reference of RTH, or elements running from 1 to the final element. That means up to 6th. So I will use this MATLAB indexing, page 1, show this. And for the capacitor, we need two inputs. One of the CTH1, the temperature value, the capacitance value, an initial temperature difference. I will call it T-ini. That means initial temperature. Let's also show this. And remember, we have 6 pairs. That means we will need 5 of them more. So it's pair number 2, 3, 4, 5, and 6. Before I forget, let me change the names to 2. This is number 3. This is number 4. Five. And the last one is number 6. So we're done with the variable initialization. We need to connect. So remember that this was our thyristor heatsink network model. That means we have the initial, not ambient temperature here, the loss here, and the thermal ground. This is what we're implementing right now. Let's connect them. So it's a right mouse click and then hold and connect. Click and connect. Okay. This we'll need for measurement, but before that, we need to... Okay. We need a thermal ground. So the thermal network is created here. That means we need to feed that network with the loss. And for that, we need to build up this loss curve. That means from 0 to 1 second, we have 500 watts, and 1 to 4 seconds, we have 300 watts. We can do it easily using the step signals in PLECS. For that, we will need 3 step signals. The first one would be step time is T0. Remember, we have defined the time points as T0, T1, and T2. So it will be T0. Initial output is 0. Final output is PV1. For the second one, it would be a little tricky, but don't worry. For the second step, we need to come to 300 watt level. Let me do it first. That means we connect this one here, second one there. For that, it would be, time step would be T1. Initial output is 0, and final output would be the difference of the other two. So at T0, we're getting our first pulse to be 0, which is doing with this one, and also at the same time, at point T1, we should apply the second pulse. That means we also take plus PV2. What it will do, it will make the first pulse 0 here, at the same time with an offset go back to 300 watts. So we will have a continuous is not correct term, we will have the steps here as shown. PV2. And the last one would be, since with these 2 steps signals we had generated this stair, we also need to go to 0 at the point 4 seconds. And for that, we need to say this is times 0. Initial output is 0, and final output would be 0 as well. So we need to say minus PV2. If you don't understand what's going on, just keep watching and think why we just added different times at different power levels. I'll show you right away. Let's take a scope. Okay, here we need to connect this. So since we are feeding the blowset here, in other cases you saw this, this would represent the semiconductor losses. Either it can come from directly from semiconductors. In that case, we needed the heatsink, but since we are having that loss directly, this is also another way to implement the thermal calculations. Let's take 2 scopes here. We need to first check if our step signal is correct. Now, this is a PLECS standalone version. That means we do not have the scripting capability directly as it is done in BlockSet, but still we can take this advantage. Until now, I don't know how to run that lib script of MATLAB using this one. I tried this command, it didn't work, but we can run that M files anyway. So the name of the file that I initialized the variables in M file is examples1.1 initialization, which is exactly written here. For some simulation control, I took the variable to be tsim. This one's a standards one that I always change. Control. Okay. Let's check our pulse waveform first. Okay. Don't worry about the temperature at this moment. We'll see how to correct it. The important point here is to see if the second curve, which is the loss ones. So until 1 second, you can see here, until 1 second we have 500 watts, and between 1 and 4 seconds we have 300 watts. Perfect. Now you see some peculiar behavior. The waveforms are okay, but the values are very odd looking at this point. We need to see where the problem is. So, first of all, we need to specify the ambient temperature, which is TA. Let's rerun. I think Control T is the short for that. It's still showing a negative value. Okay. We need to check where the problems are. So I just noticed that this scope is actually showing the wrong signals. Most probably I had to do it this way from left to right. So you see the dot here, it should represent the first signal. I was expecting first signal to show the pulse waveform, and it was showing the temperature waveforms. So I just corrected. Let's see. First we should see the pulse. Let's now go back to the temperature. So I think this is a direction of measurement, but does it make that difference? Most probably. Most probably. Let me check. Okay, the orientation of thermal capacitances seems to be making a problem. What if I... Okay, a little bit of task again. So we need to change the orientation. So let's run it again. Okay, this is now better than before. This is what I was expecting. But there is still a problem. The waveform of the pulses of power losses are okay. But one problem here is that I was expecting the temperature waveform to start from the ambient temperature, but it starts from, I see it's almost 250 or 245 degrees here, initial temperature. So the problem lies in the matter that we have defined the T initials to be 35 degrees. And this 35 is then added each time. They're in serial connection. So T1 as a T1, 2, 3 for all of the thyristor pairs, they're serially connected. And if you add 35 times 6 plus 35 as ambient temperature, you should have 245 at the beginning, which is not realistic. The temperature should rise following that exponential curve from the ambient temperature. So the problem is to be solved by setting the initial temperature of the each RC pairs in the Foster model to 0. That means that's why I took two different variables here. That means if we have this Foster model defined externally, we need to initialize all the capacitors to 0 and the ambient temperature to the proper values. Otherwise, initially, it will give you the wrong result. After running the simulation again, now this looks good. This is what I was expecting as well. So at the beginning, you see the temperature was at 35 degrees Celsius. Then it follows that exponential curve to reach the peak point at 9. Let's check the value here. Show the maximum. So within these two cases, we have a junction temperature as 90.61, which is exactly what we calculated theoretically. And at the end of the second pulse, we have 81.557, which is also exactly what we calculated. Remember, we had TJ1, TJ2. So at the end of first pulse, we have 90.619, which is exactly also in the PLECS environment. And TJ2, that means the second one is 81.557. You can see these are, that means PLECS is working exactly in the same way we went through the solution. If you remember, we had this live script to go through. It exactly calculated at the end of this pulse, implements these equations, and then calculates the temperature values. I thought this would be helpful in order to fathom the importance and steps to calculate the thermal models using PLECS environment. In the future videos, it's going to be much more complex calculations, complex models of thermal networks. But I think this was the end of this solution. But remember, this calculation is valid so long as we have the pulse form of the power losses. We will also look into different calculations instead of pulse one. If we have sinusoidals or half sinusoidals load forms or the power forms, maybe it so from the machine theory, you know, there are different characteristics of loading. At S1, which is for continuous loading, S2 short time loading, S3, S4. We will see in future tutorials how to calculate the temperatures for this type of different loading. Now, for the pulse forms, the mathematical form is relatively easy. It's not much to be concerned about, but for the other forms, as I just mentioned, it's going to be a very complex mathematical model, which is I will be explaining in future videos. But thank you for watching and have a good day.